Hello everyone, welcome to Weekends with IIIT Hyderabad. In this series, IIIT Hyderabad faculty discuss their research in ECE and CS domains. I would like to take this opportunity to remind you that IIIT Hyderabad is targeting at least 25% intake of women students through the JEE mode in 2020. Special measures for women students entering the JEE through the JEE mode include 25% off on tuition fees for their entire duration of their BTech and merit-based scholarships from their second year onwards. Please visit our website for more information about the JEE Gender Diversity Pool. Now, to start today's discussion, I would like to ask a fundamental question. How are intelligent systems made by humans, such as smartphones, computers, processors, refrigerators, everything else, electronic systems, different from naturally occurring intelligent systems such as animals and humans themselves? Think about that for a second while I introduce myself. Hello everyone, my name is Dr. Aftab Hussain and I am a faculty member and flexible electronics researcher at Center for VLSI and Embedded Systems Technology in IIIT Hyderabad. I started my research into flexible electronic systems as a master's and PhD student from King Abdullah University of Science and Technology, KAUST for short, in Saudi Arabia. At KAUST, I was lucky enough to be a part of the research group of Professor Mohammed Hussain, who is a pioneer in the field of flexible electronics. I followed that up with a stint as a postdoctoral fellow at Harvard University under the guidance of Professor David Clark. Now, coming back to the question I asked, what is the difference between man-made and natural intelligent systems? One interesting distinction is that electronics that we make are generally rigid, they're rectilinear, and they're clean and dry, so to say. Whereas the brains that make these electronics are soft, curvilinear, wet and squishy. My job as a flexible electronics researcher is to bridge the gap between the man-made and the natural intelligent systems. You must have seen many electronic systems around you, like there are finished products like phones, computers, washing machines, refrigerators, microwaves, everywhere around us we have electronic systems. But inside these systems, you will generally have a printed circuit board that basically looks like this. Okay, so this is basically made out of a material that is called FR4, fire resistant polymer, and on top of it those very tiny black dots are basically silicon ICs, and these are the ICs that actually process the information, whereas that FR4 board is just there to support them and to interconnect, to make the interconnect possible. In my research group, we examine ways of figuring out material systems that can make this system flexible like this, so that we can print whatever we want on a flexible piece of plastic and still be able to get metallic interconnect through them. Obviously, with a change in material comes a change in the way it has to be processed, so that is clearly there. The problem is that the current electronics industry is completely geared towards making electronics with a particular material and process that basically form our rigid phones. Hence, to move towards a flexible electronics system, our industry will have to basically disrupt a very, very large industry. But the move towards flexible electronics, at least from our perspective, like from flexible electronics research perspective, is inevitable because we eventually want to integrate more with our electronics. That is already happening. For instance, we have Fitbits and smartphones with us all the time. We have earphones and everything. So we want to stay connected with our electronics all the time. So going towards flexible electronics does seem intuitive. Another problem with moving towards flexible electronics is you have to remember that the performance of our flexible systems cannot be lower than the conventional electronics that we're used to. Obviously, nobody wants a slower phone anymore. So we have to make sure that they are as good as the conventional electronics, as well as they last as long, if not more. So in a sense, this process of making electronic systems completely flexible actually reinvents the entire electronics industry, from materials to the process that we use to fabricate the electronics, the performance characterization that determines how well the electronics works, and to reliability, which basically tells us how last it longs. So the entire electronics industry, all the way from materials to reliability, actually has to be reinvented, which means the nice thing about flexible electronics research is that you can choose an area that you like to work in. For instance, if you really like to work on reliability, you can work on reliability of flexible electronics. So the entire field of flexible electronics is basically open if you choose flexible electronics as your research area. Now, let me give an example. One of my flagship projects has been the development of a stretchable thermal patch. The key idea behind this patch is that we put this on our skin and it heats up basically because we pass a current through it. That is very normal, like Joule heating. And I'm sure you must have seen at your homes as well. You have those back pain this thing as well, like pads for back pain management. So we looked at them and we said, can we miniaturize this so that this entire system can be woven into our fabric itself, and can we electronically control it so that we can set the temperature of our shirt, right? So we answered these questions by coming up with a process that has a thin layer of copper bonded to a polymer. Why copper? Because it's a very good conductor of electricity, and we need a good conductor to get Joule heating. Why polymer? Because we wanted to make it flexible and stretchable. The actual process of actually combining copper and polymer is of course complicated, and let's not get into that right now. But what ended up happening, once we make this process and this material system ready, we can actually make the entire heating system much more flexible and stretchable. And because the heating depends on the amount of current that we provide, we can electronically control the temperature we are comfortable with, right? So, and the nice thing about these kinds of products is that we basically go from a design all the way up to fabrication and testing of stages, which means we start completely from scratch by asking us simple questions whether it's actually physically viable to make these kinds of devices to begin with, right? So we have to do some very quick mathematical modeling and figure out whether basic physics allows us to make these kinds of devices. If it actually does, we go into some more detailed designing of the system, which basically then includes choice of material, and with that comes choice of processing. Obviously, we have to look at the constraints as well. We have to worry about availability, we have to worry about fabricability, there has to be material intercompatibility, and so on, and last but not the least, affordability, right? So we can probably do a lot of things with platinum, but we can't because it's going to make our electronics extremely expensive. So then once we are able to figure out what materials to use, what processes to use, we go ahead and fabricate the system, and then we do a lot of rigorous testing. And this is where a lot of fun is involved, because you actually get to flex your systems, stretch them and test them while they are being stretched, while they are being twisted. So it's a lot of fun. There are of course parameters to define all of those strains, but it's a lot of fun in designing these test apparatuses as well. Another interesting project that I have been actually involved in was the development of a flexible device that can be literally placed on top of your brain surface. The surface of the brain is called the cortical surface from the word neocortex, and the technique to sense anything or electrical signals from the brain surface is called electrocorticography, ECOG, which is very similar to EEG, in which they basically put electrodes on top of the scalp and get information about the brain activity. But in this case, because the electrodes are directly placed on the brain surface, you get a much more clearer signal of what's going on inside. Obviously, once you do that, you can only do it in a hospital setting, because all of these ECOG sensors these days are wired. So you have to assume that you're probably lying down in a hospital. Somebody has to cut open the skull and put these sensors there and monitor whatever activity they are trying to monitor. What we try to see is, as flexible electronics researchers, is if we can make a wireless system that can actually do ECOG, we can implant these kinds of systems in certain individuals, and then they can actually go about doing their normal business, and still we can get information and signals from them wirelessly. Obviously, this has a wide range of implications. You can, for instance, if you can get very clear brain activity signals all the time, you can actually start controlling things just by thinking about it, which is a very interesting future to live in. But there are a lot of challenges that are involved in these kinds of applications, particularly that the materials and the chemicals we use to design these kinds of systems should not affect the chemicals in our brain. That is kind of obvious. They have to be biocompatible at the very least, and they have to be also not be affected by the chemicals that are there in the brain. So the electronics has to be safe for the brain, and the brain has to be safe for the electronics. Only then the system will work for a longish duration. So these are very interesting challenges and constraints that we work with. We have to do a lot of research on material science. We have to do a lot of research on processing to be able to make sure that all of these systems are physically viable, they are flexible and stretchable, as well as they are safe for the wearer, or if they're being implanted for the person for whom these have been implanted. So it's a very wide research area, and the examples that I gave you about the brain-machine interface and the stretchable heater, I'm sure that you have seen that there are many aspects of flexible electronics that have to be taken into account. And because it's a very new field, we thought why not we come up with a course specifically for flexible electronics. So IIIT Hyderabad is actually one of the few institutions in the world to offer this kind of a flexible electronics course for the entire semester. It's a proper full semester 4-credit course just dedicated to flexible electronics. Students can take this as an elective at the moment in their 3rd and 4th year of BTech of ECE, which is Electronics and Telecommunications Engineering, and MS and PhD students who are also in ECE can also opt for this as an elective. The way I've designed this course is that there are no prerequisites for joining the course, so anybody can take it as an elective. I've basically made sure that a very fundamental intermediate or 10+2 level understanding of physics and chemistry is required, so that we can basically go through the entire the material science, the mechanics, and everything else that is involved in making these kinds of systems. What we generally do in this course is that we start with something that is a general electronic system, right? So I would generally start by saying that any electronic system would consist of a controller, a memory, a display, say a battery to run everything, and maybe some transceivers and antennas and so on. Right? So that's the general design of almost any electronic system. So what we do is we then go through each and every component and see how we can make flexible versions of these. Because if even a single one of them is rigid, you can't make the system flexible, right? I mean, once you integrate everything, then the whole system will be rigid because one of them is rigid. So you have to make each of them flexible. So how to make a flexible controller, how to make a flexible memory, how to make a flexible display, how to make a flexible battery is all that we have to cover throughout this course. We go through the physics of it, the material science of it, the processing of it. So it's a long journey. It's a very fun course to be in. One of the other things that I generally do in this course is that for various modules, I will also inform the students what are the conventional ways of making these systems and what are the conventional ways in which they work. So for instance, because it's important to know that, because for instance, you must have heard of the AMOLED displays, right, that are there on all of your phones. We have to first go through the basic design of the AMOLED display and see what the conventional AMOLED displays are made of and how they work. Once we are able to understand this, only then we'll be able to tweak the materials and processes to make it flexible. So not only would you learn about flexible electronics, you would learn a lot about the conventional electronics, at least the basics of conventional electronics themselves. For instance, how an AMOLED display works, how a lithium-ion battery works, how a solar cell works, and so on, how a memory works, and so on. So at the moment, that is all I had to say about my research and the courses I teach here. Thank you all for listening, and let me know if you have any questions through the chat feature. If you have missed a part of this video, please remember that this video will be available on our YouTube channel in a few days. So let me see if I can take some questions. So one of the questions is that please tell us about a few projects done by students in this field. So actually, that's a great question. When I generally run this course, I actually have a project component in the course itself. So everybody who's taking this course has to do a project, right? So I remember very clearly last year we had a project in which some of the students tried to make a flexible speaker. So they did that by actually putting flexible conductive coils on top of a plastic substrate so that the entire thing is flexible. And using those coils, they were able to create a magnetic field and make them vibrate, given a sound signal. And you know that vibration itself is sound. So we actually had working speakers, like they connected it to a phone, and we could actually hear, albeit not very loud, but some sounds coming out of that speaker. So it was very interesting to see that a flexible speaker could be made by students in a matter of, say, 2 months' time. So it's a vast field. I mean, and given that now IIIT also has a lot of, we are basically investing in infrastructure for Makers Lab. We have 3D printers, laser cutters already with us. So we can actually come up with a lot more project ideas, and we can actually implement them here and see them working. So one more question is, can you please tell us about the future job prospects for flexible electronics? It is a rare field, yes, that is true. But the interesting thing is it's one of those fields that is catching on. So for instance, IoT has been one of those fields, AI has been one of those fields that are already caught on a lot. Now you see that a lot of interest is there in people who know AI, right? So this is one of those fields that will be very more, like much more prominent 5 to 10 years from now. Already you can see that Samsung, for instance, has launched a flexible phone like the Z Flip phone. LG is coming out with rollable TVs, and all of these big companies, when they start investing in technologies that are actually rollable, foldable, and stretchable, they will actually look for individuals who are already trained in these kinds of fields. So it's a very nice time to enter this field. Because it's right now sort of just about to explode. So getting into flexible electronics research at the moment seems to be a very opportune time. Somebody has asked, is this lab restricted to ECE students only, or CS students can also apply? Yes, CS students can also apply to this course. We don't really have a restriction as such, but generally looking at, like I just said, job prospects in flexible electronics are prominent with companies that do research in core ECE areas. So generally, the students are interested from their part like ECE students are interested in this course. But if some CS students are interested, I would be very happy to take them. Like I said, I don't expect any knowledge or a prerequisite knowledge of ECE or anything before you come to this course. So we start with like a 10+2 based physics and chemistry to begin with. So somebody has asked, what is the difference between ECE and ECD program? So the ECE program is a 4-year program which only has BTech in it, and ECD program is the one that also it's a dual degree program. So you basically spend first 4 years of your stay here completing a BTech, and then you automatically transition into an MS by research, and then you complete your thesis and then graduate as masters as well as BTech. So it's a integrated dual degree program. All right. So somebody has asked, what are the key places in which we can, in which flexible electronics research is being done? So that's a great question. Actually, a lot of flexible electronics research groups are there in India. We have one very nice center in IIT Kanpur, known as the National Center for Flexible Electronics, NC-Flexi. We have a very good group in IISc Bangalore and IIT Mumbai and IIT Hyderabad, who are doing very good work in this area as well. So, and that's just India. And if you look at the world over, I think Northwestern University in the US does some incredible work in this field. King Abdullah University of Science and Technology in Saudi Arabia, from where I am, also does very good work in flexible electronics. As well as you can find EPFL actually does very good work in flexible electronics as well. So it's one of those areas that is really catching on, and a lot of research groups are actually investing a lot of time and effort in developing infrastructure to be able to conduct this kind of research. And you can see a lot of interest from government entities as well, like for funding these kinds of activities, because they probably see it as the future of electronics as well. So somebody has asked, what is the scope for making flexible electronics for rural areas? I mean, I guess it will percolate to all fields and all kinds of areas once we start developing some interesting ideas or product ideas or interesting solutions to some of the problems that are being faced. So it's a very specific question, I would say, but the answer to that is if you can find a problem specific to a particular geography or say a rural area that actually can be solved using flexible electronics, that may not be solved or is difficult to solve using conventional electronics, then it's a great place to be. So you can develop that solution and help out the people in the rural area. All right, I think that is all the questions we have. Thank you so much for listening in. Please remember that this is the first of a series of interactions with IIIT faculty. Please join us next Sunday for a session titled Bits, Signals and Diversity. Until then, thank you so much for watching.